Hello. So, this video we are going to be covering a personal favorite of mine, complex numbers. So we're going to introduce complex numbers and sort of the basic operations, how to deal with them, and standard forms for sort of how to write them down. So, at the start, complex numbers. What are they? So, complex numbers, it's sort of a bigger version of the real numbers, sort of like how you have rationals and then you have reals, right? The reals include the rationals but have other stuff. Complex numbers are pretty similar. So you can tell sort of a number is complex if you can write it in this sort of special form, this z equals a plus bi, where there's sort of a little note here that depending on the notation of the book or software or online, wherever you're looking at it, sometimes they prefer to put the imaginary part first, that bi plus a. In terms of sort of vocabulary, right, terminology, a, that piece that's on its own, that's called the real part of z. And the b, importantly not b times I, just the b part. So the b is called the imaginary part of z, and that's because it's multiplying against I, that imaginary constant. And so it's sort of the part that is attached to the imaginary part of the z, okay? And again, just in terms of notation, we can call the sort of set of complex numbers, or we denote it by that sort of weird, the weird looking C things. We call that blackboard C, or sort of boldface C sometimes. That's a whole other conversation. We're not going there. So this is just like, the Z for integers or R for real numbers, same deal. Okay. All right. So that's sort of what they are, how we sort of notate them. But the sort of important part is how we deal with them, right? So the real and imaginary parts, these things are dealt with as if they're sort of completely independent values, meaning you don't sort of put the A and the B together in any way. The imaginary stuff goes with imaginary stuff, real stuff goes with real stuff. So when you're adding and subtracting, that's how this sort of works, right? The real stuff together, the imaginary stuff together. But for multiplication and division, it gets a little more tricky because you end up having to sort of distribute stuff in a nice way so that you can sort of put it all back together again. So this is one of those things that we're going to sort of go through some examples, okay? All right, so addition. So if you have two sort of generic complex numbers like this, z being a plus bi and say w being c plus di, if we want to get them together, right, we want to add them together, we start by just writing it down. You don't technically need parentheses here, but I'm putting them so you can see, right, that first block is that z, second block is the w. But then we want to rearrange them, right? So we put the imaginary stuff together. So we have that bi from the z and the di from the w. And then we have that a and c, right, from z and w, but those are the real parts. So we're shifting this around so that it's real parts together, imaginary parts together. And then we can factor out that I so that we end up with real part plus imaginary part times I, right? So this is the sort of general form. Now I realize this is probably some alphabet soup looking thing, so let's do sort of a concrete example to see this in practice. So let's say we want to add 3 plus 7i and negative 2 plus 19i. So again, same idea, we're going to write it down. Technically we don't need parentheses, but just to show, right, we have one number plus the other number. Then we rearrange it so that we have the real parts together and the imaginary parts together. Then we can factor out that I, just like it were, say, an X or something, right? So we can pull that out so that we just have numbers and then put the numbers together, right? So the 3 plus negative 2, that's 1. 7 plus 19, that's 26. So I end up with this nice A plus BI looking form, right? The real part plus the imaginary part times I, right? So that's how we want to sort of end up when we write a complex number. Now, subtraction, it's pretty much the same thing. This shouldn't be terribly surprising because subtraction, right, that's one of those things you learn long time ago, right? Many moons ago, back with arithmetic, that you could make subtraction into plus and a negative or whatever. Same thing goes for complex numbers. The only tricky thing is that you have to make sure you distribute that negative, right? Because now your number is actually two different numbers, the real part and the imaginary part. So again, if we're, say, subtract minus 2 plus 19i from 3 plus 7i, right? So the 3 plus 7i, that's at the start, minus the negative 2 plus 19i. But then I have to distribute that negative, right? So I have to do negative times -2, negative times positive 19i. That gets me this 3 plus 7i plus 2 now minus 19i. But after that, it works the same way, right? So group the imaginary stuff together and the real stuff together, pull out the imaginary part, and then combine the numbers. So here I would get 5 minus 12i, okay? So addition, subtraction, not too bad. You do have to remember to distribute that negative with subtraction, but otherwise it sort of works more or less the way you'd think. Multiplication's a little bit trickier. And this is because really, in some sense, these are both binomials, right? We have a plus bi, that's two terms being added together, a binomial. And so if we're multiplying two of those things together, it's sort of like doing, right, the polynomial multiplication where you have two binomials. So we need to distribute this, sort of like that FOIL method or whatever, box method, whatever you've learned. But basically, what we're going to do is the generic sort of distribution method for polynomials. But here we're using complex numbers. So again, in a sort of concrete version, if I have that -2 plus 19i, and now I'm multiplying 3 plus 7i, now the parentheses really are important, right? Because I need to have them multiply, but I have to distribute all that stuff out. So in particular, I can take that second term, multiply it against each of the first terms, right? So I have -2 times that whole thing, that's 3 plus 7i. And then I have 19i times 3 plus 7i, right? That same second thing. And then the next step, I do that sort of thing again, where now I'm distributing the -2 across both 3 plus 7i and the 19i across the 3 plus 7i. And that gets me, right, -6, -14i, plus 57i, plus 133i squared. But remember, the whole point about I is it's this thing that is defined as I squared being -1. So I can replace that I squared with what it is, with that -1, and that's now real, right? So that tells me that I really have a -133 as that last term. I can put the I terms together, which I did here, right, with the 43i, but then I can put the two real parts together and get that -139 plus 43i, okay? So again, complex numbers, when you're doing multiplication, you have that sort of tricky first step where you have to like distribute everything out, but after that it works pretty sort of typical for, the other versions. The really tricky one, that's division. And the reason is that with division, you have to use a trick sort of similar, not quite the same, but very similar to how you learn to like rationalize denominators or even sort of get rid of sort of square roots in the bottom when you're looking at sort of various radicals with algebraic terms and things. And that's by multiplying by the conjugate. Now with radicals, they defined conjugate in a certain way, which is good for radicals. Complex numbers, they have a different definition, so I'm going to cover that here. So complex conjugate, so if you have some complex number like z, and again, we can write it as that a plus bi thing, right? Then the complex conjugate of z is this z minus bi. So you're flipping the sign in front of the imaginary part. And just as a note, we won't use this much in this class, but it does show up in other classes, and it might show up if you're looking at, depending on what book or what class you're in. This conjugate has like a very special or very specific notation. It's usually referred to as bar, so you'd say z bar here, and it's just the letter with a little bar over the top. Again, we're not terribly clever with this whole naming thing. So that's what this is saying. This is colon equals means is defined as. So this is saying z bar defined as a minus bi, flipping that sign, okay? So lots of words, but the takeaway is that when you're talking about conjugates for complex numbers, all you're doing is flipping that sign in front of the imaginary. So again, let's look at an example. Let's say we want to divide -2 plus 19i by 3 plus 7i. Well, we start by having that written right as a fraction for division. So we have this thing, but the thing is that we want to get this into some form a plus bi, right? We want to get it to that standard form. The way we do that is we multiply by the conjugate of the bottom. And the reason for this is, as we'll see, we're going to get sort of a nice result in the bottom that will end up being just a real number, which is going to be very helpful. So my first step when trying to rewrite this sort of division as the form, right, in the form a plus bi, is to multiply by the conjugate of the denominator specifically. So then multiplying, right, I just multiply the top and the bottom. But the whole thing about the bottom is that the bottom is really, I mean, I'm doing it all out so you can see it, but the bottom is really a difference of squares, right? Because it's the factored form of difference of squares. So what this is going to end up being is the first term squared minus the second term squared. But that second term, 7i, when I square it, is going to get me this, right, this negative 49i squared when I do the, right, minus that term squared, 49i squared. But remember, I squared is a real number. So this 49i squared is going to be a real number. The first thing is a real number, and those middle terms are going to cancel. So all I have left is a real number. Downside is the top is whatever it is. It's usually a mess, right? I have to expand all that stuff out and then start putting stuff together as like terms. So I can do that here, right? So I have minus 6 plus that 14i plus 57i minus 133i squared. But again, that I squared is negative 1. So I can replace that in the top and bottom where I see I squared. And cleaning all that up, I end up with 127 plus 71i in the top, all over 58. Okay, so that's, replacing the I squared with negative 1 and then just combining all their like terms. But this isn't quite in a plus b I form, but it's very close, right? And in fact, what I can do is I can take that and split it across that plus sign, right? I can have 127 over 58 and 71 over 58 times I, right? And that's in that nice a plus b I form, right? So this is how you have to actually get to the a plus b I form when you're looking at division, where in this case, right, we have a being 127 over 58 and b being 71 over 58, okay? So the whole trick that makes this work is that we end up having to multiply by the complex conjugate in the top and bottom, right? The complex conjugate of the bottom, we're multiplying the top and bottom, so we're only multiplying by 1, and ... right? A lot of expanding out, canceling, and putting stuff back together. Eventually, it gets us down to this form. Okay? All right, so what do we do? Well, we introduced complex numbers, this sort of bigger than real number set, right? So just like how you can go from rationals, right, the fractions to reals, you can go from reals to complex numbers. This is, by and large, sort of not too crazy when it comes to dealing with these things, right? The real pieces sort of stick together, the imaginary pieces stick together, and they sort of don't interact with each other. And for the most part, that's not too bad. The only time it gets sort of annoying is when you're really doing multiplying and dividing, because they're now binomials, not monomials, right? They're not single numbers, they're two numbers attached each. So when you multiply them, you have to sort of distribute everything out before you can collapse it back. And if you're dividing, in order to get it into that standard form, you have to multiply by that conjugate of the bottom in the top and bottom, right? So that is that.